Hello friends, I am Professor Vidyadhar Sagar, Mechanical Engineering Department, Tulsiramji Gaikwad Patil College of Engineering. Today we are going to be see lecture number 6 on new topic of unit number 1, Introduction of Materials and Imperfections of the Crystals. So this is one of the last topic of this particular unit, in which we are going to be see the imperfections of the crystals. Now imperfections of the crystal which generates the defects in the crystal structure causes the major defects in coming future. So what are these defects we'll see. First is lattice vibration, second is point defect, then third is line defect, fourth is planar defect. So lattice vibration is what that atom are not satisfactory in their designation lattice position but are vibrating about their mean position, and the frequency of vibration depends on the temperature. So basically what is the lattice vibration, which causes due to the frequency of vibration and changing in temperature during the solidification of metals, right? So that lattice vibration causes cavities, cracks and defects in the crystal structure of metal, which will be causes a major flaws in the future. Then the next defect is the point defect. Point defects will be subcategorized into four main categories. First is vacancy, then self-interstitial impurities, then substitutional impurities and interstitial impurities. And third one is a line defect. Line defect we subcategorize in two categories. First is edge dislocation, second is screw dislocation, and then fourth category of the imperfection in the crystal is planar defects. So let us see one by one. So next one is the point defect, and point defect which explains that the defect is occurred at a particular point in the crystal structure. Now what is the crystal structure? Crystal structure is made up of number of unit cell or the layer of atom which is arranged in sequential or in random manner. The defect will be occurred at the point which is considered the defect is occurred at the position of the atom. If the one atom is absent from its location, we call it as a vacancy defect, and the atoms is overlap on another atom, we call it as self-interstitial defect. If the atom is get absent and the foreign impurities get trapped inside in between the layers or the vacancy of the atoms, we call it as substantial impurities of the atom. If the foreign impurities get trapped inside the space in between two layers of atom, that impurity we call it as the interstitial impurities of the atom. So that's all about the point defect. Then let's see about what is the line defect. The line defect basically occurred in the line where the number of atoms lies in a particular line, and this defect will be occurred in basically two main categories. First is edge dislocation and second is the screw dislocation, as shown in the diagram, where the line dislocation, where the edge dislocation, edge get inserted into the number of edges of a particular space lattice, which causes the imperfections of the crystal structure. And the screw dislocation, in which the two layers of the space lattice get moves towards opposite to each other and get form a screw like dislocation. Now then planar dislocation or planar defect, we call it as a planar or the surface defect, arise due to the change in stacking of the atomic planes during the solidification or mechanical or thermal treatment. The change may be of the orientation of stacking or sequence of the plane. The planar defect will causes due to the defects in at particular level of the plane of the space lattice. Right? So that's all about the imperfection of the crystal. Next topic is the Miller indices. Now what is the Miller indices that we have learned in previous some classes, but the Miller who discovers the planars, that planes we call it as a symbolical planes, and the Miller was the famous metallurgist who was discovered that plane and kept in front of the world in form of a new research. So Miller indices are the reciprocal of the fractional intercept, which is plane makes with the crystallographic axis. These reciprocals of fractional intercept which the planes makes with the crystallographical axis. The reciprocal of the fractional intercepts are converted into the integers by common multiple of the certain number. So the Miller indices can be defined into the number of planes. One of the plane we can define as shown in the diagram as one triangular plane get intercepted into the three number of vectors at A, B and C, and the intercept we call it as a P, Q and R. Now when we formulate these intercept and vectors in form of the Miller indices, that Miller indices we call it as a reciprocal of the fractional intercept. So we can take these intercepts as a P, then the vector where that intercept gets occur is A, then Q upon B, comma R upon C. And when we take the reciprocal of these intercepts, we will get A upon P, comma B upon Q and C upon R. Then when we multiply these fractional intercepts with a common integer, that is a unity, that unity we call it as a lattice parameter, it will become 1 upon P, comma 1 upon Q and 1 upon R. So this is all about the Miller indices. Then we will see the mechanical plastic deformation. That mechanical plastic deformation gets classified into two main categories. First is a slip and second is the twin dislocation. So slip dislocation basically occurred as shown in figure as the upper layer get dislocated from the lower layer from its original position, which forms the slip dislocation. The twinning dislocation basically occurs due to the shearing forces act towards opposite to each other. So that's all about the mechanical plastic deformation. So that's all about the first unit, and we'll see in next lecture in second unit new topic. Thank you very much for the today's lecture.